we are going to see about the Hall experiment. Okay, so in this experiment we are going to determine the Hall coefficient of a given semiconductor, right? So let us get into the experiment. The experiment consisting of an electromagnet connected to a power supply, and there is a constant current power supply. This is the sample holder which will be connected to a gas meter, and this one is a semiconductor, is a 4-probe semiconductor where the terminals are proceeding here. So these are the apparatus required. So before we start the experiment, now we have to nullify the electromagnets. So what I am doing now is, let make the power supply to 0 and calibrate the gas meter such that the gas meter shows nullified reading. So this is the first precaution we have to do before performing the experiment. If any reading is proceeding here, there is a button called set 0. We have to adjust this button in order to maintain the digital gas meter reading as 0. So with this, let us start the experiment. Now I am slowly introducing the Hall probe into the 2-pole pieces of an electromagnet and ensure the gas meter show a positive reading. In order to achieve this, I am rotating the probe so to make a reading positive. Now you can see some positive reading is visible to you, right? So now I am slowly setting the electromagnets in order to make 1 ampere reading in the power supply of electromagnets. Now, so I have maintained the power supply of electromagnet as 1 ampere and noted down the digital gas meter reading. The digital gas meter reading shows 1.048 of kilo gas. So to convert that kilo gas into gas, you have to multiply this value by 1000. So here similarly we have already noted down the value and converted into terms of gas. Initially it was showing us 0.1647 and then I'll convert it into kilo gas, which will be given by 1647 gas, right? So let me write once again down the value that is available in the gas meter. Now it is showing 1.047 and therefore if you multiply it by 1000, it will be giving us 1046 gas. I am going to write the value as 1046 gas. Okay. Now you come back to the constant power supply. Now you adjust the knob such that you can fix the Hall current to a certain value. Correspondingly, you can note it down the Hall voltage. Let me fix the Hall current as 0.5. So it is showing 0.55. So I have to note it down this. It is 0.56 and the corresponding Hall voltage is 10.8. Similarly, let me move the knob. Before that, I have to place the sample in between the electromagnet. So let me place the sample exactly in between the pulses of an electromagnet and ensure that these two will not touch with each other while taking the reading. Okay. After placing the sample into an electromagnet, I am noting down the reading. It shows that for 0.56 it is 12.3. It is 12.3. Now I increase the current to 1 milliamp and check. Okay, now it's showing 1.26 and the corresponding Hall voltage is 27.3. Similarly, let me increase to 1.5. So it is 1.5. It is 1.5. Now, so I note it as 1.44 and the corresponding Hall voltage is 33.1. Similarly, I am going to perform for 2, 2.5 and 3 and the corresponding values are noted. For 2 it is 42.9. For 2 it is 42.9. For 2.5 for 2.56 it is 55. It is 55 and finally for 3 finally for 3.03 it is 65. So the values are noted in the corresponding table. So based on this value, a graph is plotted between the Hall current and the Hall voltage by taking the Hall current on x-axis and the Hall voltage on y-axis with the variation of 0.25 on each and every unit. In x-axis it will be vary in terms of 5. The values are plotted here. These 2 points are crossing the straight line. A slope is taken between these two and the points are noted. A value of dy is 22.2 by taking the difference of y value between these 2 points. The value of dx is 1.05. If I divide this value, I am getting 21.143 at the outputs. Now let us calculate the Hall coefficient. In order to calculate the Hall coefficient, we have to use this formula, that is RH is equal to VH into T by B into IZ. Here VH and I can be taken from the graph, which is given as 22.2 into 10 power minus 3 and 1.05 into 10 power minus 3. The thickness of the material is taken from this sample and it was already mentioned as 0.67 micrometer and hence it is taken as 0.67 into 10 power minus 3. The Gauss value B is nothing but the Gauss value, which will be identified initially in the tabular column, which is given by 1046, and those value can be written here. By substituting these values, if you calculate, the final value will be obtained in terms of 8.6009 into 10 power minus 6. In order to convert the Gauss into Tesla, you have to multiply this value into 10 power 8. Finally, you get 0.86 into 10 power 3 centimeter cube Coulomb inverse. So this is the Hall coefficient of the given sample, from which we can calculate the carrier concentration, which is nothing but N is equal to 1 by RH into E. By substituting the value of E as 1.6 into 10 power minus 19 and the RH from the previous value, the value of carrier density is calculated as 7.266 into 10 power 16 per centimeter cube. Similarly, we can calculate the carrier mobility, which is nothing but the RH value into conductivity. Here, the conductivity of the sample is 0.1. and the RH value is 0.86, and therefore if we multiply 0.86 into 10 power minus 3 into 0.1, then it will be 0.086 into 10 power minus 3, or it is 860 centimeter square volt inverse second inverse. This is how the carrier mobility is calculated. Thank you.